experiment, we are bombarding a box of hydrogen with white light. So here we just push on, and these are photons, whatever they are, photons of different frequency. That means white light has all the different colors of light. And we're looking at the light that this box of hydrogen is emitting, and it appears to be that there are very specific wavelengths of emission. This is called the emission spectra of hydrogen, right? Wavelengths that are even beyond and below the visible spectrum of light. So this is what we can detect with our eyes and more sensitive tools as energy coming out from the interaction of light with matter, in this case matter represented by a box of hydrogen gas. So what is this experiment telling us about the atom? What we're going to do is also important is that when we change the intensity, that means the number of photons hitting per second, the spectra of absorption or emission is always the same. So it seems that it is independent of the intensity of light, but the frequency of emission only depends on the frequency of the light that is hitting the hydrogen atom. If we want to do the same experiment with monochromatic light, that means sending only one color, we have to hit the right color, the right frequency, right? We have to be very careful to hit the right frequency in order to get that kind of emission spectra. But let's forget about this. Let's continue with white light. It is independent of the intensity. The spectra of emission has certain frequencies or wavelengths that are, like we said in class, these are the fingerprints of hydrogen. We can identify hydrogen, for example, as being in an atmosphere of a planet or of a star by just looking at this spectra of light coming from hydrogen clouds that are between the source and the observer. Now let's look at the different predictions for this model. So the most simple model, the billiard ball, that means an atom made of some kind of solid stuff, should bounce all different colors. There shouldn't be any specific preference for any frequency, as you can see here. So obviously this model was, it could not explain many things. It could not explain the electricity, but it could not also explain this strange interaction between light and matter. Thomson's pudding, if the photons actually hit the plum in the pudding, whatever that is, a charge that is inside the pudding, then the emission should be of only one color. Only one frequency should be emitting, because the plum is limited to the size of the pudding. So there is no way this could emit higher frequencies or longer wavelengths, longer wavelengths, right? The wavelength has to be associated only to the size of that pudding. So obviously this was not an efficient model to explain the interaction of light and matter. The solar system doesn't resist any analysis here, so the interaction of light and matter could not be explained with the solar system model. And of course, many other things cannot be explained with the solar system model. For example, the fact that the electron does not spiral down to the nucleus. So we have to look at Bohr, de Broglie, and Schrödinger as the three models that have some kind of attempt to explain this interaction of light and matter. Bohr has these ideas. There are certain quantum levels, certain energy levels, and the electron is jumping between one or the other in discrete manners, spontaneously. Let's slow it down so you can see this. You see the electron in the first orbit, all of a sudden at the same time appearing in the last orbit because it emitted a photon. And then it emits a photon and comes down, emits a photon and comes down. We're looking at the electron here, emits a photon and comes down. So the photon that the electron is emitting comes from this different wavelengths, and that has to do with the absorption and emission of certain frequency that allow the electron to orbit in certain quantum levels. This is Bohr's explanation to this interaction of light and matter. The mystery is, okay, how can a photon disappear from one orbital and appear at the same time in another orbital, like you just saw, jumping from here up here and then decaying down here, and then we follow the electron here. Boom, decaying down here and emitting a photon, right? But this explains very well the predictions, so it's a successful model. De Broglie associated a wave, instead of an electron, an associated wave. He introduced the hypothesis of wave-particle duality. And the electron has different, or the wave has different frequencies associated to it. And depending on the momentum of the collision of the photon that is absorbing that momentum, that is transformed into another resonant frequency. Let's look at this in high speed. So we're thinking of electrons as wave that resonates in certain frequency, more or less in the same way as waves resonate for certain frequency inside pipes. A beautiful mathematical model that explains, a very simple model that explains that interaction between light and matter, the de Broglie hypothesis. Beautiful, beautiful. And then Schrödinger introducing the wave function. There's no matter, it's just probabilities, waves of probability, and the positions of an electron are determined by the probability of finding an electron. So the implications of this model is that everything is energy, and energy collapses into a particle when we observe it. So these are three models that work to explain this interaction of light and matter. Which one is better? Which one is true? These are all models. The truth is always mysterious, but we'll use them because they work to predict the behavior of the interaction of light with matter.